search insert position. So to solve this problem, we need to know what binary search is. Binary search is exactly what the problem wants us to do, trying to insert an element given a sorted array. So let's illustrate this with an example. Let's say we have a sorted array 1, 3, 5, 15, 23, and we are trying to insert 16. Now, without going into the algorithm, what should the final result look like? It should look like 1, 3, 5, 15, 16, 23. And 16 will occupy position 0, 1, 2, 3, 4. So the final outcome of this algorithm should output 4. So how do we do this, keeping the result in mind? Well, the point of binary search is to reduce the search region of where to insert the element. And to do this, we rely on two pointers. A pointer that points to the leftmost bound of the search area and a right pointer that points to the upper bound of the search area. So once we have this, we want to consider the middle element of the search area. So the middle element is 5. 5 is less than 16. Therefore, 3 and 1 can be ruled out because they will not be the positions in which we insert 16. 16 has to be inserted in position 4. And obviously, positions 0, 1, 2 will not work because the elements in those positions are all less than the target. So therefore, we update the search bound to only consider 15 and 23. So we put the left pointer to be 1 above the middle pointer right here. Now, what is our middle pointer? Well, our middle pointer is now going to be between 15 and 23, but there's nothing in between, so we just round down and make the middle pointer point to the same position as L. And middle is 15. 15 is less than 16. Therefore, let's repeat the algorithm, right? The algorithm says if the element at the current middle position is less than the target, then we have to update the lower bound. The lower bound gets incremented 1 above the middle counter. So we move L to right here. And we can rule out 15 as the position to insert our target 16. So now we only consider 23, where the left and right pointer point to the same element, 23. Therefore, the middle element is also 23, which is larger than 16. Since this is larger, that means the right pointer has to go down by a position, or the position of the M. So if M is here, then M moves the right pointer left by 1. Now, this violates the rule that the left pointer has to always be less than or equal to the right pointer. Therefore, we stop. Now, what are the values of our pointers after the search? Left is at position 0, 1, 2, 3, 4. So L is equal to 4, right is equal to 3. We know the final answer should be 4. So the final answer has to be the left pointer, meaning after we search the entire array and nothing works, we should return the left index as shown. And I believe this was a recurring problem or question on the Leetcode forum. So I hope this illustrates why we return the left pointer if the while loop does not work. And with this understanding, let's go on to program this up in Python. So let's just basically translate the logic into code, right? So we always maintain a left pointer, but remember, the search region at the very beginning is going to be the entire array. So let's put the left pointer to be the index 0, and the right pointer will be the length of the array minus 1, because that's denoting the last element within the array. So according to the logic, while the left pointer is less than or equal to the right pointer, we're going to find the middle element. The middle element is found at the middle index, which is going to be L plus R double divide 2. Double divide basically truncates a decimal and rounds down a decimal. So we have the middle pointer at L plus R divided by 2. Now, if the nums M is equal to our target, then we just return M because we found the index. But if the target is going to be less than the nums at the position, what does this mean? This means that everything to the right of the array is going to be not the index we want to insert it because it's too big. So let's update the right pointer to be n minus 1. And the vice versa holds true if the target is greater than nums m, right? Because in this case, that means everything to the left is not okay. So L is equal to m plus 1. And just from the example from what we've seen, we know that if all else fails, we return the left pointer according to our logic. So we just run it, and let's see how many results pass. Everything passes, so let's submit. And we have beaten all of the runtimes. So that's the solution with minimal memory and minimal runtime.